Hello and welcome to Logistic Regression Intuition. In this video, we'll be discussing a popular classification technique known as logistic regression. We'll start by explaining the concept of logistic regression at a high level, and in the upcoming video, I will give you a practical example to provide a better understanding. So let us discuss the meaning of logistic regression. First, let us review the linear regression before covering the logistic regression. So in the video about linear regression, we learned how to predict outputs on a continuous spectrum. We used an example of predicting revenue based on outside air temperature. To demonstrate, we took the example of an ice cream stand and predicted that at a temperature of 20 degrees, the daily revenue would be around $500. So as the temperature increased to 35 degrees Celsius, we increased the revenue to $700 or $800 daily. We obtained a linear model using a linear regression, which is represented by the equation y equal to mx plus b. This equation is essentially a straight line. It is important to note that the outputs were a continuous spectrum, meaning the revenue could range from $100 to $1000. Logistic regression is a statistical model used for predicting binary or categorical outcomes, which means there are only two possible classes, class 0 or class 1. For instance, when taking an exam, you can either pass or fail, or when playing the lottery, you can either win or lose. Similarly, during a yearly body assessment, you can either be healthy or sick, and so on. So, logistic regression is mainly used for classification purposes to determine the probability of an event occurring. Therefore, it is entirely a different approach compared to other regression techniques. So when faced with a problem to choose a solution, should we use linear regression or logistic regression? The first question you need to ask is, what does the output look like if it is continuous or binary? If you have a multiple values or parameters such as revenue and you need to predict something continuous like salary, then you may need to use linear regression or even polynomial regression to ensure that the output is also continuous. This will allow you to more accurately predict continuous outcomes. When it comes to classification, logistic regression is the way to go if your output is binary. For example, 0 or 1, pass or fail, or whether a customer bought a car or not. So here linear regression won't work. Let's consider a basic example to illustrate the concept. The independent variable represented on the x-axis is the number of hours of studying, which can vary from 1 to several hours. The dependent variable is the outcome of the exam, which is classified as pass or fail, labeled as 1 and 0 respectively. So on the x-axis, we'll plot the hours of studying, and on the y-axis, we'll plot whether the student passed or failed the exam. So let us plot some points to better understand this. For example, if a student studies for 1 hour, he is likely to fail, which is represented by a y value of 0. Similarly, if the student studies for 1.5 hours or 2 hours, they are still likely to fail as their y value would also be 0. So after 6 hours, you will be able to pass the exam. Therefore, this is 0 and this is 1. Let's say that I have no knowledge of logistic regression. So if I were to use these data points and apply linear regression, I would try to fit a linear model to them. However, this approach would certainly fail miserably and results will be really very bad. So let me try to clarify what I mean. So in our system, the output can only be 0 or 1. We do not have any value in between such as 0.5 or 0.7. The continuous nature of such values is not required in our case. So our output is bounded between 0 and 1, which means it is saturated. Our linear model has a major flaw as it can go unbounded and produce unpredictable results, so it can't take on values as high as 2 or 3 or as low as -2, -3 like that. So given these limitations, we can conclude that our linear model is not suitable for classification and should not be considered as a viable solution. So that's why we move from linear to logistic regression. We wanted to modify our straight line and give it a curve. So we decided to change our function in such a way that it looks like the desired shape. By doing this, we'll be able to explain our problem more effectively and accurately. To clarify, the equation for logistic regression differs from the one we have previously seen. So instead of y, there is a logarithm on the left and same part as before on the right. The crucial value here is p, which represents the probability. So let us examine the logistic regression curve. The logistic regression curve is also known as sigmoid curve. But how does it work in practice? So let us consider two new observations, someone who studies for 4 hours and someone who studies for 7 hours. To use logistic regression, we used to project these values onto the curve. The logistic regression model tells us the probability of someone passing or failing based on their studying hours. For instance, for a student who has studied for 4 hours, there is a 41% chance of passing. Similarly, for someone who has studied for 7 hours, the probability of passing is 82%. In some cases, we can use these probabilities as they are. However, in most situations, we need a binary outcome as a yes or a no as an answer. To achieve this, we split our curve into two. So anything written above this middle line has a probability of 50% or higher and will be considered a pass and projected as a binary 1. Anything written below the middle line has a probability of less than 50% and will be considered a fail, and it will be projected as a binary 0. Based on this logistic regression, we can conclude that the student who studied for 4 hours will not pass, while the student who studied for 7 hours will pass. So this is where our points end up. Similar to linear regression, multiple independence variable can be utilized. For example, the book you are referencing, the educational background of your family. So like if you are stuck somewhere in your lesson, your family can help you in that, and the number of individuals studying with you can also be considered. Additionally, other types of variables can be incorporated as per the specific use case. So thus the equation will appear as follows in this scenario. So even though we have a curve that fits our data, we cannot be certain that it is the best fit. As with linear regression, there may be several curves of this shape that could fit our data. So how do we determine the best one? The answer lies in calculating the maximum likelihood, which involves examining each data points carefully. So for example, we have this green data point and there is 18% chance that he will pass. Similarly, for this data point, there is a 48% chance. For this data point, there is a 93% chance. And for this, 95%. And for this point, we have 98% chance. I will just plot a different graph for red points. For this point, so there is 93% chance of getting pass. So for the red point, we want a fail. So we'll subtract it from 1. So 1 minus 0.93. Similarly, for this point, it's 1.1 minus 0.75. For this point, 1 minus 0.48. For this point, 1 minus 0.13. For this point, 1 minus 0.16, and this 1 minus 0.1. So this all red point shows the likelihood of getting failed. So we are subtracting 1 minus the passing percentage. So our likelihood will look like this. So we'll multiply all the points and we'll calculate the likelihood. So although there is more complex procedures involved, the basic idea is to compare the likelihoods of various curves. For instance, if we were to start with the logistic regression model shown in the graph and calculate its likelihood, we would end up with a specific value. Then it went to the next curve and it calculated the likelihood to be this one. Then the next curve, the likelihood was this. So as the data moved on to the next curve, the algorithm calculated the probability of the curve being the best fit. So this iterative process continued until the algorithm finds the curve with the maximum likelihood. So this curve is considered the best fit of all the curves, and this is how the logistic regression calculates maximum likelihood. So this was it from the logistic regression. So I hope you have liked this video. Please subscribe to my channel and I will see you in the next video. Until then, keep thinking data science.